Today we have Professor Alma R. Méndez. Is an associated professor of physics and mathematics at the Universidad Autónoma Metropolitana, UAM, Cuajimalpa, in Mexico City, and a member of the National System of Researchers, SNI. She has a bachelor of degree in physics and a PhD in science physics at UAM Iztapalapa. Her work focuses on the kinetic theory of the traffic flow and the relativistic gases. So thank you again, Professor Alma, and it's with you. Thank you again.
Thank you. Did you see my presentation? Yeah.
No, it just yes, it was working, but now I can't see it.
Oh. What about now? Yeah.
It is coming. Okay. Now I can see it. It's working.
No.
It is working. I can see it. Okay. Thank you.
Thank you. Okay. Good afternoon to everyone, and I want to thank the organizers for the opportunity to be here today to talk about my research work. This work is in collaboration with Wilson Marquez, here present in UFPR, and with Rosa Maria Velasco Belmont from Universidad Autónoma Metropolitana in Mexico City. Okay, I am going to talk about some of the effects of the finite size of vehicles in the theoretical description of traffic flow. And well, as everybody knows, the study of traffic flow in highways represents a very big challenge. And this problem is mainly interesting when vehicular density is high enough to produce congestion. So we are interested in these situations where we have congested situations. So the goal of this presentation is to show how we established a theoretical flow density relation, starting with a modified version of the Prigogine-Herman-Boltzmann kinetic equation. And we are considering that vehicles has a finite length, and I am showing some advances with the related with multi-lane traffic. The results obtained in this model will be analyzed and compared with with very recent empirical data, and we show how our relations allow us to obtain some important quantities in traffic flow, as the traffic capacity or the critical density or the desired velocity. Okay. First, I'm going to talk about what is the fundamental diagram. Maybe some of you know what I am talking about, but for people who don't know what is this diagram, I'm talking about this. Well, the fundamental diagram is a functional relation between traffic flow and the traffic density measured in the stationary state. And the mean velocity as a function of the traffic density is also known as the fundamental diagram. So these two relations are known as fundamental diagrams, and both must be in the stationary state. Here we have the first fundamental diagram presented by Greenchilds in 1935. Here we have the mean velocity as a function of the traffic density, and we have a linear relation. The velocity is a decreasing function of the density, as shown here. And in the case of traffic flow, we have in the vertical axis the traffic flow, and in the horizontal axis the density. As we can see, when the density is close to is zero, we have zero flux. But as the density increases, the flux starts to increase until it reaches a maximum value, and then the larger the velocity, the value of the density, the smaller the value of the flow, because vehicles start to interrupt each other. So, well, this was the first fundamental diagram, and it must be said that all the fundamental diagram allows very important information, because it allows us to understand the typical behavior of traffic flow on a road. And wait, please interrupt me if you need me explain something a little more, please. Well, a typical empirical fundamental diagram looks like this one in here. Here we have the flux as a function of the density. And as you can see, there is a lot of dispersion in this region of the diagram. And this Kaufman asserts that this scatter observed in the fundamental relation is due to a flaw of the old methodologies, because it is difficult to imagine a single curve that describes all this data. This scatter is frequently attributed to a combination of non-stationary traffic states. Sorry. But why it is important, the fundamental diagram in traffic flow? Well, it is important because it is used usually as a source of information for more sophisticated models in traffic flow theories. Also, since Green-Shields relation was proposed, there has been many attempts to measure and construct the correct theoretical fundamental diagram. But the traffic flow relation is difficult to measure, and however, new methodologies seems to be able to overcome some of the problems, as the need to seek for stationary or homogeneous conditions. This has been observed by Kaufman in a very recent reference given here, it most of the fundamental relation curves are fit to a cloud of aggregated data, and as a result, the fit is poor. In fact, it is required prior assumptions of the curve shape before fitting. So we are now considering, because in the measurements there are vehicles of different lengths and in different states. This is the principal difficulty. Recently, it has been observed that many of the parameters involved in the flow density relation depends on the vehicular length. So much of the traffic modeling should be reformulated in order to explicitly take into account the length of vehicles and to consider also inhomogeneous traffic. And it is in a very recent research, it has been shown that multi-lane and multi-class models are important because sorry, because we have to consider the length of vehicles and vehicles with different length show different behavior in the traffic flow density relation. Okay. Very recently, another important fact is that has been observed that drivers predict and adjust their speed based on driving distance on the lateral vehicles. So it is important also to consider multi-lane traffic because the spacing in the lateral lanes can produce or can change the stability of traffic. So we are laterally aborting this problem at the end of this talk. Here I'm showing the fundamental relations obtained empirically by Kaufman in 2050. And as can be seen here, we have different relations or different curves for vehicles of different length. Here, the red dots are for vehicles between 18 and 22 feet. The green dots correspond to vehicles between 22 to 28 feet. And the purple here is from 28 to 38 feet and etc. No? Okay, as we can see here, for different sets of different lengths, we can obtain different curves for the fundamental relation. Here it is shown the mean velocity as a function of the spacing. Spacing is the inverse of the traffic flow, no, traffic density, sorry. And we have, and Kaufman obtained also different curves for this relation. Here again, the red corresponds to set from 18 to 22 and so on. Okay. Well, as I've said, we want to construct a theoretical fundamental diagram that considers that vehicles have finite length. So we are generalizing a kinetic equation known as the Prigogine-Herman-Boltzmann equation in the sense of Enskog. So we are considering that traffic is moderately congested. And in this approach, we are considering two additional assumptions to the typical kinetic models. First, we consider that the interaction frequency is enhanced by a factor t. And second, we evaluate the kinetic kernel in the actual position of the interacted vehicles, which is x plus d, where d is a kind of effective length of vehicles moving with velocity v. And t sub s here is a safe distance, it's a safe time. So the kernel is evaluated in x plus d. Our model reads like this. In the right side, we have the drift term. We have an acceleration term to the desired distribution function f sub 0 in a relaxation time tau. And at the right, sorry, we have the interaction term this first term is the gain of dots in the fast space of the distribution function, and this other term is the loss of dots in the distribution in the fast space. Here, as you can see in blue, chi is a function that increases the frequency of collision, and we have evaluated the distribution function in the actual position of the collision. The parameters that appear here, or the quantities appearing here as chi, for example, chi is a quantity that depends on the density. The larger the value of the density, the larger the value of the density. When the density approaches to the maximum density, this term in the denominator approaches to 0, so the chi quantity grows to infinity. So as the density grows, the more congested situation, the chi factor also grows. For the case of P in here is the probability of overtaking. So 1 minus P is the probability of not be able to overtake the vehicle in front. So this is also a function of the density, and when the density grows and approaches to the jam density, which is the bumper-to-bumper density, this quantity approaches to 1. So the probability is 0 when the density grows. For large values of the density, P is close to 0. Vehicles cannot overtake the vehicle in front of them. And when the density is small, the probability of overtaking is close to 1. Okay, and finally tau, the parameter appearing here, which is a kind of relaxation parameter, depends on also on the probability of overtaking. When the probability is close to 0, in a very congested situation, the parameter tau grows to infinity, so it's very difficult to reach the desired distribution function. But when the probability is close to 1, this relaxation time approaches in diluted situations. This relaxation time approaches to 0. So the distribution function, the single distribution function, approaches to the desired distribution function. Okay. Well, in order to obtain the fundamental diagram from this model, we have solved this equation for the steady and homogeneous state. And the obtained solution is this one here in equation 5. Here appears the desired distribution function, and we have these two parameters, gamma. Gamma is a combination of the chi parameter, of the probability of overtaking, and from the density, and tau. So all this quantity, gamma, is a function of the density. For sigma appearing here, we have that sigma is 1 minus gamma u, where u is the mean velocity given by the first moment of the distribution function in here. And we know that in here, in this distribution function, the quantity sigma plays a very relevant role because, as everybody knows, the distribution function cannot be negative. So this parameter sigma is positive, and the velocity is also positive. So in order to have a positive distribution function, we have to take to be very to have care with the value of sigma. In fact, given the expressions, given sigma in terms of the expressions for chi, p, and tau, it can be verified that sigma approaches to 1 when the density approaches to 0, and the sigma could be negative in the case that sigma grows. So since sigma cannot be negative, it is possible to define a critical density that we are calling rho sub c, which separates the transition between the free and congested regimes. In the case of the free regime, sigma must be larger than 0, and in the case of the congested regime, sigma is equal to 0. Okay. Now, in this expression here, we also have to give a prescription for the desired distribution function f sub 0. So in this case, we are considering that f sub 0, which is the desired distribution function, is a gamma distribution function given by this expression in here, where the parameter alpha appearing here is a measure of the aggressiveness of drivers. This distribution function for typical values of the in traffic has the shape of a bell, as shown in here, and is centered in this case at the mean desired velocity u sub 0. The normalization condition for the density, even in here, and which is the 0 order moment of the distribution function, can be rewritten in this form, where this function in here is the exponential integral function. And as we note, this is as an expression for this quantity, sigma alpha over gamma u sub 0. And in order to obtain the fundamental relation, we must solve this equation, but it can be solved only numerically. Okay, but in our model, we have note that sigma plays a very relevant role and separates the free and the congested regime, and it also allows to make some assumptions and consider some things in order to avoid the numerical solution of this equation. So in the case of the congested regime, sigma is equal to zero. So what one can obtain from expression here from this expression sigma equating to 0, this expression, one can obtain the fundamental relation, which is the flux as a function of the density given here in equation 8. This is one of the main results of our model. We have an analytical expression for the for traffic flow as a function of the density in terms of the model parameters q sub 0, which is the traffic capacity, the tau sub s, which is the safe distance, the critical density, which can be obtained also analytically, and L, where L is the length of vehicles. On the other hand, for the free regime, we have that sigma is larger than zero, and to avoid the numerical solution of the expression here, we have made some assumptions, and we have observed numerically also that that traffic flow is a linear relation of the density in this regime. And with this approximation, it is possible to write the fundamental relation in this regime, as in this form, and define the traffic capacity q sub 0 as the desired mean velocity for the multiplied by the critical density. These results from equations 8 and 9 are shown in here. Here we have traffic flow as a function of the traffic density for different values of L, where L is the length of vehicles. So the solid curves here are our results from expressions 8 and 9. And the dots here are Kaufman empirical data obtained in this reference, from this reference, sorry. And as can be seen, this curve here is for vehicles of length between 18 to 22 feet. The next curve, this one, is for vehicles from 22 to 28 feet. This one in here is from 28 to 38 feet, and the last curve here is for vehicles between 56 to 68 feet. And as can be noted, we have different curves for different vehicles for different sets of vehicles of different length. Here is the mean speed as a function of spacing, is the other relation that I shown in another slide. Here, again, we have the solid line is our theoretical prescription, while dots are data from Kaufman. And we see that our theoretical description and Kaufman empirical data have a very, very good agreement. We have taken these parameters in this table from Kaufman, and we have set these values for the model parameters. Okay. What is important to note here is that with this consideration that the vehicular length is important, and we have to separate the fundamental diagram for different vehicular lengths, we know that we have very clear and very separated curves. And this is, we have not this dispersion in the fundamental relation, and the empirical data is in agreement with our model. Okay, we have observed also that a kind or a universal like behavior when the data is expressing in dimensionless variables. Here we have all this data shown here are Kaufman data in dimensionless variables. It is the traffic flow is expressed in this form. is the traffic flow over the traffic capacity, and the density is multiplied by the length of vehicles. So this is a dimensionless quantity. And when data is expressed in this form, we note that all data of different sets from 18 to 22 to 22 to 28 and 28 to 38 collapse in a single set of data. And when we express our theoretical model in the same form, we know that there is an excellent match between theoretical description and empirical findings. In fact, from this universal traffic flow diagram, from this universal flow density diagram, one can obtain a kind of critical density, reduced critical density zeta sub c, which has the value 0.2 for all considered set of data. Okay. Okay. As I mentioned before, multi-lane traffic is also important because it is observed that when vehicles have not enough space in the lateral lane, there is the problem of this is a kind of unstabilizing. Well, the traffic is unstable. So we are now considering also to model multi-lane traffic, and we are considering Phillips model, which has this form, is very similar to the one to the Prigogine-Herman-Boltzmann equation, but in this case, here appears n, which is the number of lanes in the road, and these quantities g and this quantity chi and tau here, and the probability of overtaking are functions not only on the density, but also on the number of lanes in the road. Here we have some advances. We have these two curves for a road of 2 lanes. This is the case of the solid lane, and this other is the case, and the dot lane is for 4-lane road. And well, it is observed that there are 2 different curves, and we have 2 different traffic capacities, and also 2 different critical values for the density. So this is some advances of our modeling of multi-line traffic, and that's all. Okay, now I'll give some concluding remarks. We have constructed a non-local kinetic model in order to consider that vehicles have finite size and observe the effects of inhomogeneous traffic. Okay, we have obtained the theoretical fundamental relations for vehicles of different length and observed separated curves for vehicles of different size. And this is very important because now we have no dispersion observed in the first on the old empirical observations. Our model reproduces empirical fundamental relations for vehicles of different size, and we have that with our model we can derive some parameters as the the mean desired velocity or the save time, or some critical values as the traffic. Sorry, here I have as the traffic density and the reduced traffic density. Okay, we have also observed a sort of universal behavior only in the case that we express the fundamental diagram in dimensionless variables. And this behavior has been observed theoretically as well as empirically. So we can construct a single fundamental relation with where there is no observed data dispersion. And finally, a similar generalization of the Phillips model is being carried out to establish a multi-lane model. Thank you so much for your attention.
Thank you, Professor Alma. Who wants to start the questions? I have two, but I will wait the people that are watching us. You can just hang the hands or open the microphone. Let me do the first question, and the people, everyone has some time to think about. But you showed us on slide that you have a curve about the aggressivity of the drivers. All right. That curve, it is there is some match in empirical evidence, or it is just an assumption to the aggressivity of the drivers.
You mean the distribution function?
Yes, you have a distribution function about the velocity, I think, and this is there is some relation with the aggressivity of the drivers, or
Yes. Yes. Sorry. Wait, just a second.
Okay.
Do you see my presentation? Yes.
Yes, for sure. I think it is.
This one.
Yes, exactly. This curve that you put in the right side, it is related with this aggressivity. You put the aggressivity in your function and obtain this curve of distribution.
This distribution function is obtained by from other models in traffic flow. In fact, we have obtained this expression analytically from a kinetic model also that considers that vehicles have aggressivity.
Okay, but this factor just goes from 0 to 1, or not, because in your expression you have alpha minus 1 there. So
yes, no. Alpha is larger than 1.
Larger than 1. Okay.
Larger. Yes.
Okay.
Yes.
And you just feed it to adjust to your data.
Sorry, I didn't understand.
You just get the value for this alpha to adjust for the data that you.
It is obtained from some experimental data.
Okay.
Yes, the value of alpha is experimental.
Okay, because I was thinking about that maybe this value it can change from, I don't know, if you have data from one country or to another, or from, I don't know, even in the same country, from one region to another, because yes, maybe this alpha has a well-defined mean value, but should have a larger dispersion also, or not?
Yes, the value of alpha can be must vary with depending of the kind of drivers you have. This is in this case we have considered a typical value obtained from experimental data related with the variance of the velocity.
Okay.
Yes, but it must change with the kind of the kind of drivers you have. Yes.
Okay. Thank you. And anyone else?
May I just say something?
Okay.
Oh, Alma,
Yes.
can you show the results concerning the free and the congested regions? These both
This?
solutions. Yes.
This one
This.
or
Yes. Okay. This. Tiago, can you hear me?
Okay. Yes, I am hearing.
Okay. I just want to mention something here. This solution given by equation 9 that correspond to the free region, okay?
Okay.
Is we can only write the flow a linear function of the density when the value of this alpha parameters is greater than 1.
Mm.
Okay?
Okay.
So we show that by numerical solutions that when the parameter alpha goes to a value above 100, what is observed experimentally, this flow goes linear with the density in this free region, no?
Okay.
yes.
And in the congested region, the parameter alpha does take into the solution, no? The solution does not depend on the alpha parameter, does not depend on the aggressiveness of the drivers, because in the congested region, all drivers drive at the same way, no?
Okay. Because yes, I see. I was wondering about because if there is um, I don't know. You should have this alpha large, like 100 or so, but it is prohibitively that you have this alpha value near 1, for example. What would be the solution? What would you observe if you have a really low alpha?
A low alpha.
Yes.
I see.
Well, I think that when alpha is very small, the gamma distribution function approaches to an exponential
Yes,
distribution
yes.
function, and in this case,
Yes, it would tend to zero that expression, or because the gamma it is something over gamma. So if this explodes, like yes,
yes,
maybe.
No, alpha must be greater than 1.
Yes, yes,
yes,
okay. But if it nears 1, like if you go to a really really calm regime for to
in
say.
fact, alpha is from the order of 100.
Yes, yes, yes. Okay.
Yes.
And I think there is another important point, Alma, that we should
Yes.
mention is that if you go to the curves.
Yes. Okay. Here.
These curves, no?
Uh-huh.
These results, these empirical results obtained by Kaufman follows from a road near the San Francisco Bay
Okay. Yes.
in California, no? And
Yes.
this road has 10 lines, no?
Oh.
5 lines that go in one direction and 5 lines that go in another direction, no? And if you take this into account, that's why we are searching this multi-lane model. You can improve these results, no? Because our model, this model here, just have 2 lanes, no? And
Yes.
it's not compatible with the real situation, no?
Yes, of course. Yeah.
I see. And you have tried like a situation that you just reduce the number of lines, like or improve the number of lines. Like there is some way that you can put in your model the number of lines in a flow.
I'm sorry, I didn't understood the question. No.
Your solutions, it is for 2 lines, okay?
Yes.
2 lanes. So if you have 2 lanes, there is a way that you can put in your model, or you're thinking about a way to put something in your model that just give this information about the number of lines, the number of lanes that you have in a road.
Well, as I mentioned, we are now considering the multi-lane model of Phillips. There is explicitly the number of lanes, but in the case of the results shown here in this plot, we are not explicitly considering the number of lanes, but in this other model from Phillips, n is the number of lanes and is considered explicitly.
Oh, I see.
I don't know if that's a question.
Yes. But I think that if you could use your model to achieve this, because this is a subtle different model. So if you could consider directly in your model.
No, it's the same model, Thiago. The difference is that you can to take into account a multi-lane, no? More lanes. You have to change the form of the probability of passing. No?
Okay, you add this term, this extra term there. Okay, I see.
No? You have to change the form of P.
Yes.
And
okay.
then you can add more lanes. What we cannot do is change the number of lanes during the movement of the vehicles, because this will lead to a non-stationary solution, and our model is for a stationary solution. No?
Okay.
Yes.
Okay, but yes, okay. I will I will wait someone else to make questions, because I was thinking if you have like a 3-lane to 2 lanes, okay, maybe in this situation you could have some stationary situation, but I don't know if
No,
how.
because you are making a bottleneck, no?
Yes.
And you cannot have a stationary solution in this case, because the flow will change during the time, no?
Okay, okay. Okay, thank you, Professor Alma.
Okay. Good afternoon.
So if we don't have any more questions, I think that we can thank you again, Professor Alma, for this nice talk. And if anyone has questions, please you can just enter in contact directly with Professor Alma, or to send us, and we put both in contact to I don't know, see these questions. Okay, so thank you again, and good afternoon.
Bye bye, pessoal.
Bye.
Bye. Alma.